In 3, 2, 1. Okay, hi everyone. Thank you for joining us in. Let me mute myself on YouTube so that I don't get that. All right, I'm back. Hi everyone. Thanks for joining us. This is SJAA's monthly speaker series once again, and for those of you who haven't joined before, I will just give a brief introduction before we start. The club has been around for many years, over a few decades now, and we are based in San Jose, California. But this was one of our events that we used to do around full moon, right after our board meetings. And then the pandemic happened, so we had to figure out how to continue going. And the way we have figured it out is by doing this event virtually. This was one of the ones that was easier to transition, I guess, into. So the idea is pretty simple. We like to bring some new knowledge to our member base and to anybody who is an enthusiast, I suppose, not just our members. But if you're interested in becoming a member, I would highly recommend going to sja.net and become a membership is just $20 for a year. And also we have our own meetup channel or meetup group that you can join and find out about our upcoming events over there. Like the schedule is always kept up to date for the most part. And we are starting to do our star parties again, which is really cool. It's slow rolling back into it kind of thing, where we have some electronically assisted astronomy happening. We have people showing views from the telescopes again. And these events are starting to happen every month or so again as well. So that's another reason why I would recommend checking out Meetup or our website to see what's coming up and what you can join, because in addition to the night star parties, we also have daytime star parties to see one star we have, which is the sun, and the cool sunspots. So it's just a very active club, and that's one of the fun things about being involved with it. I think I will also put in a shameless plug for asking for volunteers. We always need help. Our speaker here was just mentioning how he has his own astronomy club that he works with in Sacramento. And so, yeah, definitely organizations like these don't run without help from people. So if you are interested in helping out, just please reach out. And then we would love to get some help from you. So with that, I will come to our topic for today, which is a topic that interests everyone pretty much, black holes. Fascinating subject indeed. And I'm sure you might have come across a name, Sagittarius A, at some point in recent past. And it was a big news that, oh, we got a picture of a black hole. So today we have a speaker who's going to educate us a bit about that. And Awanish Mishra, we're very happy to have you here. He has a lot of experience in science and tech industry as well. And I mean, what was curious to me is you did your degree in chemistry with a minor in quantum physics, which is a very difficult subject in my opinion. And then you have gone on to do other science work after that. And even if now you're retired, as you told me, you're still doing active astronomy, outreach, and astrophotography as well. So thank you for joining us, and I will hand it over to you to start your talk. Thank you.
Well, thank you so much for that introduction. And I'm thrilled to be here. And I will say that about a year ago, I moved to Davis. And so I've joined the Sacramento Valley Astronomical Association, but I still remained a paid member of San Jose Astronomical Association and have been for quite a few years. So I'm thrilled to be able to participate, and I'm thrilled to be able to give this talk. So without wasting any time, Today's talk, I'm going to talk about black holes and actually about stellar life cycle briefly, quickly, and go into black holes, and then discuss the Event Horizon Telescope and how it was used to image 2 black holes so far, and more that'll be coming down the pike. So let's go ahead and get started. First of all, I think many of you are aware that Don Matchholes passed away this last week. He was a great guy. I got to see him last November, give a talk at our club, and I had a couple of chats with him on email, and he certainly enlightened me a lot. But, you know, if anything, I'd have to say he was a really sharp guy, and a very a gentle soul. And I appreciated that a lot about him. Clearly shocked by what happened. So may he rest in peace. So tonight's agenda, we're going to talk about from gases and dust to stars, how they're formed, stellar life cycle, our sun. And that part I'm going to try to go through fairly quickly. I'm sure a lot of you are familiar with this. And I'm happy to, I'm keeping it at a fairly high level. And then we can dig in the deeper based on questions, and you can also reach out to me by email as well. And then I'll jump into black holes and the Event Horizon Telescope. So with that being the case, let's go ahead and get started. Really quick, as she mentioned, I have a chance to study science and be in the tech industry. But what I really want to point out is that I love my beagles. Oh God, they're the greatest things in the world. And I love cold weather. I've had a chance to go down to Antarctica, and also using a Russian nuclear icebreaker to the North Pole. Unfortunately, in both of those cases, and when I was in Antarctica, too cloudy to take any photographs. And of course, in the North Pole, well, it was 24 hours a day light. So I tried to do some solar photography, what did work out. But I'm excited about the time I've had over the last few decades, and now that I'm retired, I can focus on astrophysics, quantum mechanics, and relativity. Anyways, enough about me. So let's talk about the formation of stars. Okay, so there are countless stars in the universe, and in the visible, in the known universe, and the Milky Way contains over 200 billion stars. Some have said 150, others say up to 400 billion. 200 billion is a nice, safe number to say, and let's be proven wrong. So stars are formed, as probably you know, by from hydrogen gas and dust clouds, which are part of dark nebulas, cold nebulas. Temperatures are around minus 430 degrees Fahrenheit. That's in the 10 to 20 Kelvin range. So they can form individually within this nebula, or they can form as clusters in stellar, what are called stellar nurseries, which I'm sure you've seen, like Hubble images of the creations, the pillars of creation, which will show you that. So typical density in a nebula is fairly uniform, but not quite uniform. And that changes things a lot for us. With that, we can form stars. Slow-moving material allows gravity to eventually, as they come into contact with each other, to overtake, and they begin to clump despite their random motion. And slowly these clouds begin to shrink under their own gravity. And as time goes, they become denser and denser and heavier. And when things begin to compress, they begin to heat up. And slowly these clouds begin to get hot. And when that happens, you're on your way to possibly forming a star in these cloud fragments, these clump fragments. And the temperature and density will eventually reach a point where the ignition of a fusion reaction occurs. So when I say, the burning of certain gases or ignition, what I mean by that is thermonuclear fusion will occur. And this can take upwards of 10 million years. When the core temperature reaches about 10 million degrees Celsius, a protostar is born. Now I'm kind of giving you the highlights in the life cycle of a star fairly quickly because I want to get through this part of it and get onto the more meaty stuff. When this happens and the star is born, you enter a new phase in its life cycle. But at this point, The star is basically fusing 4 hydrogen atoms into a helium atom. This is what happens when we drop a thermonuclear bomb, a hydrogen bomb, except we do it in a very uncontrolled way on Earth. We're trying to do it in a way, the same way as the sun does it, to get as a fusion reactor to give us essentially limitless power, very low cost as well, because we can get the isotope hydrogen we need directly from seawater. In any case, this nuclear fusion process is most commonly known. There's a couple of different cycles, but it's most commonly known as a proton-proton chain reaction, which is really interesting in its own way. But the mass of 4 hydrogen is slightly more than the mass of 1 helium atom. And the difference is then converted into energy by an equation that's familiar probably to everyone, E = mc squared. And that's a lot of energy that's produced by a very small amount of mass. The entire pathway, which you can look up on Wikipedia and other sites, is multi-step, fairly complex, but it gets the job done. And there's a bit of, in a star like our sun, what's known as quantum tunneling involved, so that statistically enough of it can happen so that the sun can shine the way it does. But that's a whole nother talk. In a simplified PP chain reaction, you have these 4 hydrogen atoms. They go through various reactions here, and each of these little yellow exploding stars are actually bits of energy that are formed, and in the end you end up with a helium atom and lots of gamma rays, and therefore the energy that's produced. So that process begins using the PP chain reaction. But once fusion is established, the star enters slowly its main sequence star, actually enters it fairly quickly. And of course, as we all know, bigger stars, hotter stars live shorter lives, right? If you're hot, you're big, you're doing all these things and moving along really fast, live fast, die young. And then smaller, cooler stars live much longer. So we keep that in mind. And currently, from what we understand, about 90% of stars are in their main sequence phase. In other words, the universe as we know it is about 13.7 some odd billion years old. And since the first stars formed, many have died out, obviously. They've produced heavier elements, they've done all these other things. But currently, we are, most of the stars are in their main sequence phase and can continue being in that phase for billions, tens of billions, hundreds of billions of years. And they come in all shapes and sizes, right? All sizes. Shape is all the same, spherical. Betelgeuse, as you may have heard, could have already exploded. Could have exploded 700 years ago. We won't know about it. It could explode today, but we won't know about it for 700 years. But things are changing there. It is ready to go supernova. Give you an idea, that's our sun. There's a little dot in front of that word sun. So a lot of stars are a lot bigger. There are smaller stars of our size as well. And these stars can all be categorized as O, B, A, F, G, K, M. Now, when I was in high school, I took a class at De Anza College in astronomy, my first one. This goes way back, 1979, many years before most of you were born. But the professor said, the mnemonic to remember that is O, be a fine guy or gal and kiss me. O, be a fine gal and kiss me. So that's how you remember the star classifications, where O is the hottest and M is the coolest. And there are subcategories to them. You can get a B, 2, B3, B7, O3, so on and so on. So they can get very complicated. There is a class of L, dwarf stars. They're dark, red, cooler stars. Some of them have enough mass to support sustained nuclear fusion, but many of them are substellar brown dwarfs. So, oh, be a fine gal and kiss me lovingly. So there you go. There's your mnemonic. If that offends anyone, I apologize. But our sun happens to be a class G2 yellow dwarf star. That's it. That's what we have. That's what we look at every day. And there's also a diagram in astrophysics, a key diagram that all astrophysicists look at, and I'll show you that in a second. It plots luminosity, temperature, and classification, so we can learn a lot about stars and where they are in their life cycle. In fact, HR diagram is known as the Herzberg Wrestle diagram. Came about a little over, I don't know, probably about 100 years ago. It's a preeminent diagram for astrophysicists. Critical information about stars, as I mentioned, and it indicates and provides information on all types of stars. It gives you their brightness, it gives you the type of star it is, it gives you their surface temperature. With this, you can learn a lot about the current stage in the life cycle of stars at, and so on. And of course, when you're looking at a brightness of one solar units, that's our sun, and we're class G2. So basically, we fall right there, and we're in the middle of our main sequence phase, which is this. This is a very exciting diagram, trust me. A main sequence star can sustain itself for billions of years. And once the hydrogen fuel runs out, they'll enter the later stages, and then they're on a death cycle at that point. Once hydrogen is gone, there's a bunch of things that'll happen depending on its mass. It's all about mass. And then it'll continue on until it reaches its terminal stage. Typically, they follow two paths to death that we're going to talk about. There's side routes, and there's a few other things that can make it very complicated, but we'll focus on two areas. One, as hydrogen is depleted, the star then begins to start fusing helium to form other elements like carbon. This is the first path. All right. Now, when this happens, then as helium starts to fuse, it's going to increase the pressure, and it's going to cause the star to expand. You've heard of the term red giants, which is what will happen to our own sun at some point. The outer layers will slowly drift away because they're so far from the central point of gravity, and then it'll leave behind ultimately, after it goes through a process, a small white dwarf. So a low to average mass star, meaning like our sun, billions of years later, will become a red giant, will then eventually die off as a white dwarf. When it's a white dwarf, it is no longer generating energy of any kind. The second path is what supergiants, large stars, follow. Here, after depleting hydrogen, they'll begin fusing helium into carbon, into nitrogen, oxygen. There's a bunch of different processes. CNO cycle, there's a point where it'll enter what's called the triple alpha process, and so on. But ultimately, it'll result in forming iron. And that's it. Iron is the killer of a star. It takes a lot more energy to start fusing iron than you'll ever get back out. It will kill the star very quickly, and it's over at that point. Now, we can talk about in my other classes I've taught, we'll talk about how other elements are made, but you can get that through supernovas and collisions of neutron stars, collisions of stars, and things like that. But here in this process, iron as far as it goes. No more energy is produced, and the star collapses in a matter of seconds, and this results in a supernova detonation. And then the resulting core will either be a neutron star or a black hole. What I mean really by that is this. In the low mass stars, when it becomes a white dwarf, it compresses, and we'll talk about how big it is, to the point where electrons are holding it up. That's known as electron degeneracy. It can't crush it any further. In a neutron star, the electrons can be forced in to the nucleus, reacting with the protons to form neutrons and energy and all that, and you end up with what's known as neutron degeneracy. You can't compress it any further. With the black hole, all bets are off. So this is sort of the quick and dirty approach to what happens with the two path that the stars can take, and it's all based on their mass. Anybody have any questions or anything like that? If you do, you should feel free to chime in, or you can put it in the chat, or we can talk about it after I finish. So those are the two paths generally for all stars, but let's talk a little bit about our sun real quick. And as we all know, it is the most important star in the universe, period. I don't care about any of the stars. I do care about our star, and I care about all stars. And if you believe in the multiverse or have subscribed down that road, well, it's still the most important star. So about 4.6 billion years ago, cloud of dust and gas coalesced, as we talked about earlier, and it collapsed under the influence of gravity. Fair enough. So the compressed gas heated up. Now, this is all about our own sun. And the cloud began to glow in infrared and become eventually and quickly became a protostar. When I talk about quickly, I'm talking about millions of years, which is really quick. When you're thinking of on a time scale of billions, we're talking about tens of millions of years. So it happens very quickly. And up to 500,000 years later, it enters what's known as a Tuturi phase. And this is pre-main sequence. In this phase, gravity causes the center cloud to squeeze tightly, pressure and temperature. It kind of goes through this expansion, compression, back and forth phase as things start heating up more and more, and thermonuclear fusion is started. And light in the form of gamma rays are emitted. A lot of times in this talk, I'm going to mention light. And what I mean by light is not just visible part of the electromagnetic spectrum. Everything is light. Radio wave is light, is a type of light. Gamma rays are light. These are all photons, and they're different parts of the energy spectrum. It just so happens that something on the order of 0.001% of the electromagnetic spectrum is something our eyes can detect, which is the visible part of the light. Whereas the bumblebee can detect ultraviolet as well, and different animals can detect different parts of the spectrum. So in this case, a lot of gamma ray energy is generated. The outcome of all this entire process, going through the Tuturi phase, is a newborn star. And up to about 30 million years later, now I have seen articles that say a few million. They don't specify what that is. I've seen 10 to 20 million. I've seen as much as 30 or more. But about 30 million years later, I'll accept that from a professor of mine, the sun entered its main sequence phase. So it went from the Tuturi to pre-main sequence, and now entered the main sequence stage. And it's been in that stage for billions of years. The outward force, meaning from the fusion process that wants to blow the star apart, is balanced by the inward pressure of gravity. That balance is keeping the sun extremely stable and spherical as it is. This is known as hydrostatic equilibrium. That second photo, I just simply have to put into all my talks because about 18 years ago, that's the first photo I took of the sun with an old Canon camera and a poor man's homemade solar filter. And that isn't stuff on my lens cap. I mean, my lens, those are actual sunspots. I was so thrilled. I took my first, and I didn't blind myself as my wife said I would. So there we go. Now, the sun currently consumes about 600 million tons of hydrogen to produce helium. 600 million tons per second, okay? Currently, our star is about 71% hydrogen and about 27 some odd, nearly 28% helium, and the rest are trace elements that were captured during its formation and or leftover from previous stars. In case you're not aware, our sun is a daughter or granddaughter star from something else that blew up, and the remnants of that formed more stars, and that's where we're from. Our star is not like appears the driven snow just created out in the blank boonies on its own. In about 5.4 billion years, so even though it's burning 600 million tons, it's just mind-boggling. It's going to continue doing this for another 5.4 billion years. Then the fuel will become exhausted. And then what will happen is, if it can't generate that outward pressure, gravity will cause the core to be crushed and become smaller. Well, as soon as you start compressing it, pressure and temperature will rise, and it'll be sufficient for helium to be converted to carbon. And this creates an outward pressure, and the sun will begin to expand into a red giant star. To kind of give you an idea, here's where we are currently, and these are the inner planets. And when it reaches the red giant stage, we can debate whether it'll go past Earth and hit Mars or not, but we'll know in 5.4 billion years. But that's essentially what's going to be happening. So Earth will not be more than likely around, and even if it doesn't absorb the Earth, life on this planet will definitely be over. Everything will be boiled off from the oceans to the atmosphere. And then it'll enter the final phase, which will last in this red giant about 120 million years. The sun will repeatedly shrink, heat up, and back and forth, and it'll start shedding material, and the shrinking back and forth will go for a period of time. And it's known as the asymptotic giant branch stage. So it's an interesting part of its life cycle, but it's at its end. When all helium is converted to carbon, basically, our star is not big enough to fuse things into iron. It's going to stop. It's beginning of this what's called the CNO cycle, and it'll stop at carbon, and at that point the core collapses and the pressures will soar, and it'll have insufficient mass to go beyond that, and it'll essentially be a dead star known as a white dwarf, and it'll become the size of Earth with about 75 to 80% of its mass. We know this will happen because we can see Sirius B, Procyon B, Van Manen star. There are other stars out there that are white dwarfs. So it's a very curious outcome, but ultimately our star will die as a white dwarf, and the surrounding gases that it does emanate away from it will form a planetary nebula. The core will shrink down, as I said, down to the size of Earth, and then it'll simply dissipate away, and the naked white dwarf will be left to cool down. It is not, there's no engine in its core, there's no fusion energy, anything else. It's simply just really small, hot, and dense, and like 1 cubic centimeter weighs over 700 billion tons, and it'll simply stay that way for the next several trillion years until it cools into what's called a black dwarf, and it's over. Okay, so that'll be the end of that. So in summary, you have a nebula, and protostars are forming, and their gases exist, and low mass stars will end up as a white dwarf, and higher to high mass stars will go through a supernova process and end up as neutron stars or black holes. And that's the primary outcome. And as I mentioned on this Herzberg-Russell diagram, if we are sitting right here, how are we going to end up here? So there is a process for that. And so where we are now, and we're going to end up through this sort of mechanism, we'll follow this kind of path and work our way around and end up dead as a white dwarf. And that'll be the end of everything as far as our solar system is concerned. The remaining outer planets will simply become, well, I wonder if they'll continue orbiting. I'll have to think about that. They should be able to, even if though it's a white dwarf with most of its mass. Anyways, any questions at this point? Otherwise, I'll move on to black holes. I want to be cognizant of everyone's time as well.
So actually, I mean, Awanish, I have a question that came in YouTube channel, so I'm going to relay that because this
Okay.
person says they joined late and they're going to leave early. So like,
Okay.
it would be good if they're still watching to answer their question.
Okay.
How long does the supernova process take at each stage? Also, I have heard the sun is nearly perfectly spherical. How much does the sun's rotation affect its obliteness?
Well, it is okay. First of all, as far as that whole process of going back and forth, or are you talking about for a large star supernova? When that occurs, when it reaches iron in a matter of seconds, it can collapse on itself and detonate with about 40% of the mass of the star going out at extremely high velocity, even a significant, not a significant, but a good fraction of the speed of light. It can blow up, and it'll blow up just once like that. What's left behind for a supernova size star is going to be turned into either a neutron star or a black hole. So the process of exploding will occur very quickly, but material can be sent out and it will go out and emanate for several light years potentially as well. So it can, what appears to be a gentle, you see these rings and they've been going on for, thousands of years, but the explosion itself happens very quickly. The second part, what was the second part again?
Hang on. It is, I have heard the sun is nearly perfectly spherical. Yes. How does the sun's rotation affect its obliteness?
Well, interestingly enough, if you look at pole to pole and equator, it's only about 13 miles on a star that's 840,000 miles in diameter. So it's extremely round. It's one of the most perfect spherical shapes that mankind knows of and naturally occurring. So it like I said, it's about a 13-mile difference, and Earth is more actually. And so the answer is one. I agree. It is one of the most perfectly rounded objects out there, and the difference is very little. Because it's rotating, it's not rotating at some huge rate. And so it's not going to cause it to just oblate out on the sides where it's 10 or 20% difference or anything like that. I believe that's the case. Okay. All right. Black holes. Well, what are black holes? As I mentioned earlier, large stars, when they die, can become a black hole. That is the end result of their death. And it collapses effectively into a point, a singularity, where we don't know exactly, but it's zero volume, and this results in densities approaching infinity. Why? Because density is mass divided by volume. If you divide something by zero, it's going to be infinite. And I say we think, we know, we feel, but the reason we don't know is inside of that and near that region, our math, our physics breaks down. So if we can't understand it from a physics perspective, we can't tell you exactly what's going on. We've never been able to, as you know, get up next to a black hole and do measurements and do any sort of detection. And in fact, the reason for this talk is about imaging it for the first time. So that's all we can do. And the source, and they're also sources of some of the strongest, if not the strongest, gravity fields there are. John Wheeler, a physicist, gave black holes their moniker, or gave them that name in a lecture in 1967. Black holes were predicted to exist as a result of Einstein's theory of general relativity. They were also alluded to that somewhere in the 1700s. I forget who was the guy, and I should know this, but I forgot. But so the concept of black holes existed before, but certainly with Albert Einstein, he predicted their existence. So it's a location in space where gravity is so strong, because of that, not even light can escape. So you take a star like the sun, light just goes out, right? Production occurs at the core of the sun. It takes 150,000 years doing a random walk problem to cross 400,000 miles to the surface of the sun, and then boom, at the speed of light in 8.4 minutes at 300,000 kilometers per second, it's here on Earth. No worries, it's going to work. On a neutron star, which has a lot of gravity, much smaller, and we're not talking about neutron stars, but imagine a star that's 50% bigger than our sun, the size of Manhattan, about a 12-mile radius, 12-mile diameter city. That's how big it is, okay? It can curve light. It can bend light, very much so. Then comes a black hole. Instead of 12 miles, imagine it being 3, 10, 100 billion times bigger than our sun, but in a volume that's a singularity. And it's a huge star with a tremendous amount of gravity, and you reach a certain point where not even light can escape. So that's what a black hole is capable of doing. So you can't see it directly. See it as in visible. There is this little black spot here. There's a point of no return where you just cannot see what's going on beyond that point. Our math, our physics, quantum mechanics, general relativity, all of that break down. They typically form some stars that are 3 solar masses. The M with this little symbol means solar mass. 3 times the mass of our sun will lead to towards a black hole. Below that, you're going to get a neutron star. Below that, you're going to get a white dwarf. And here it shows it more like 7 or 6 or 7, but greater than 3 is capable of it. And then you move on from there. Theoretically, micro black holes can exist. That's a different type of black hole. And it was thought that that might happen when CERN was turned on and the planet would be gone back in 2011, whenever it was that they were starting to do those experiments. But it turns out the planet is not gone. The black hole wasn't formed and didn't swallow us up. But they can theoretically exist. Big ones can be billions of solar masses. Here you're looking at a black hole in a galaxy. The black hole is 4 light days away. Think about it. There's Neptune's orbit. Look at the size of that black hole. And the central black hole of the Phoenix cluster. Well, there's our entire solar system. And the central black hole is huge, billions and billions of times the size of our environment. Yes, well, Alan has a note there, so yes. The center of our galaxy has a large black hole as well, which we're going to talk about in a second. So what's the quick anatomy of a black hole? Well, you have the singularity, which is the central high density area, infinite density area, general relativity, quantum mechanics breakdown. I can't stress that enough. This is why, we as in humanity, as in scientists, don't know exactly what's going on in there, and we just have predictions and observations. The event horizon is the radius. It's a sphere. It's not the black hole event horizon is a sphere, and that is the point of no return. If something goes past a certain point, it will take greater than the speed of light to get out. And as we all know, nothing travels faster than the speed of light. There's the photon sphere, which is a curved path of photons near the accretion disk. And it is highly curved because of the gravitational forces around this black hole. And You know, if you're at the photon sphere, you could be looking straight out and see the back of your head, the way light is bent and curved around. The innermost stable orbit also exists, which is where gases just past the accretion disk are circulating, but once it enters that region, it's going to start working its way in to the black hole to increase its mass further. And that's because it's not a proper, those jets you've also heard about, I don't have it on this diagram, are not a property of the black hole. They're the result of material getting munched up by the black hole. And further out from that will be the accretion disk, which is the superheated dust and gas that is circulating. Now remember, a question I get asked is if the black hole is the sphere thing, the event horizon is sphere, why isn't everything around it? Because as we all know, it's like taking a pizza. As you start flipping it, it'll flatten out. As material comes, it begins to flatten out. You've got a bunch of different things occurring here, conservation of angular momentum and other things. So it is a form, it is a disk that forms around the event horizon, the sphere. So that's the basic anatomy of a black hole. Now, how are you going to detect it? Through perturbed motion of nearby visible objects, right? When something gets close to it, companion stars. Fortunately, there's a lot of binary star systems out there. And, you know, it's all about like Star Wars Tatooine. But if one of them happens to be a black hole, well, it could affect the other one. And that one you can see because it's a bright burning star. Mass loss will occur. It'll wobble. Sometimes you see a star all by itself, not realizing there's a black hole next to it, and it's wobbling around doing things that it shouldn't be doing. Its motion doesn't look like an independent star, so you're able to detect it by inference that way. Spinning or other aberrant motion will occur. So there's all kinds of different little properties they can look for. There's also gravitational lensing, which causes the bending of light, and you can see things behind the star, magnification, and you see doubles, and that's been proven, and that was fully predicted by general relativity. Gravity will bend light, and that was proven he published the work in 1915. The technology and the timing didn't occur, or was available to prove it, but in 1919, Eddington, during a solar eclipse, proved it. So, you know, Einstein, boy, what a guy. Emitted radiation, right? When you see that accretion disk form, as material gets close, it starts to get accelerated, rotated. And we're talking about some of this rotation occurring not at just really fast, like a satellite around Earth. We're at 25,000 miles an hour. We're talking about things moving at 25, 30% the speed of light, massive speeds. And it emits X-rays and a whole bunch of other radio waves, gamma rays, and so on and so on, lots of X-rays. So what do? We're out there, we look at radio telescopes, image in M87, which is the Virgo cluster. M87 is a big elliptical galaxy with trillions of stars versus our spiral galaxy, which is much younger and has hundreds of billions of stars. So it definitely has a big black hole out there in M87, and we can look at it through Hubble telescope optically and through infrared, and we can view it through X-ray telescopes as well. There is X-ray sources using the Chandra X-ray telescope and others that'll give us information that what is this X-ray source? We can't see anything, but there's an X-ray source there, which is a telltale sign of it being potentially a black hole. And this is a simulation of gravitational lensing that can occur. It was easier to show this as an example than to bring you a photograph and try to demonstrate it that way. So that's what a black hole is, and this is how we detect it. So in summary, For the black hole section, stars with greater than or equal to 3 solar masses can become black holes. Many stellar masses, many are stellar solar masses, meaning anywhere from a few solar masses to less than 100 are known as stellar mass black holes. And then you have supermassive ones that are greater than 1 million, many billions of solar masses. Hard to fathom that. Many billions. You could fit 3 million Earths inside of our sun. Imagine a star being 1 billion times bigger than our sun. And then black holes, as it turns out, could be at the center of most, if not all, galaxies. So that takes care of the black hole section here as to what they are and how we can detect them. That's important because before you try to go find one to take a picture of it, you need to know that there's a black hole there. So we've got these various methods to detect them, how they affect objects around them, how they affect space around them, how they bend light and gravity, the way it works, how they the gravitational field around them. It's really interesting stuff. So how do we image a black hole? Any questions at this point? Because then I'll finish up here, and then the next 10, 15 slides are on imaging. And this is really a cool part. So if there are no questions, I'll continue on, but feel free to interrupt me if you have any questions. So they're really hard to see, right? We've already talked about that. You can't get out there with a camera of any kind and just snap a picture of them. JWST is out there, but it's really not going to be able to see a black hole. Even the one in the center of our galaxy, which we're going to talk about, it'll see a blob. That's it, okay? Because its resolution is not good enough to see a black hole. So we need something even bigger and more powerful. It requires specialized non-optical telescopes because it's not the light that's the most important part. There's other energies being given off, X-rays, radio waves, and so on, that we can look at this black hole through different types of telescopes. So because it's optically invisible, well, the event horizon and beyond, we image the energetic material at various different parts of the electromagnetic spectrum, electromagnetic radiation. So this, in order to do anything like that, this requires a big telescope as large as a planet, as large as Earth, and bigger. So, but we can do it, right? And we have done it. So let's take a look at how we do this. We use something called the Event Horizon Telescope, okay? The Event Horizon Telescope Array is a virtual telescope. It's designed to see radio waves. It's not one big telescope the size of Earth, but we can make it into behaving like one that's the size of Earth. Now, before I go on, I want to mention again, it's all about angular resolution. The ability to resolve faraway objects is how small can your eyes or your telescope's eyes or whatever discern various sizes. That's what matters. So angular resolution is critical to observing any of those things. The first one we wanted to image was the black hole at the center of M87. And I haven't been able to find a great reason why did we pick M87. But I can tell you this, that like I said earlier, it's a big galaxy. It's an anchor galaxy in the Virgo system. It's an old elliptical galaxy. So it's got a huge black hole in the middle of it. It's got trillions of older stars and all of that going on. So at least whatever, for being out there, it's big. It is 55 million light years away. So its angular resolution is 43 micro arc seconds. So if you look at things around you, 360 degrees, 1 degree has 3,600 arc seconds. This thing is 43 millionth of an arc second, micro arc seconds. So it's really tough to see. So we need a telescope that can resolve at least 43 million arc seconds, right? That makes sense. Well, the human eye can resolve 40 arc seconds. Hubble can do 50 milliarc seconds. Okay, 50, 43 millimicro. So Hubble, well, this black hole is 1,000 times smaller than what Hubble can see. All right, JWST can do 7. So 7 times better, but still not good enough. So over 140 times too small. So humans can't see it, Hubble won't be able to detect it, and JWST can't detect it. At least not that one. The Event Horizon Telescope, going back to it, which is the primary focus now, is composed of as an array of a number of different radio telescopes across the world. So you've got in Arizona, in Hawaii, Alma, ESO, you've got one in Antarctica, you're looking at Spain. The blue ones are new ones that are coming online, and there's one coming in Greenland. But ultimately, imagine if this was a lens, I mean, a telescope lens, and this is the end of it, the aperture. All of these little telescopes can collect data, and then we can synchronize them. That's what forget it. You'll see it in a second. Why can't I pronounce it correctly? But they're composed of a number of these satellites, and they're independent scopes that are synchronized. These are existing radio telescopes that are now linked together, and they're synchronized down to the billionths of a second, a trillionth of a second, using atomic clocks, so that in interferometry, if I take, if there were two detectors and they're looking at the same things, they see things at different angles. But if we know exactly when they're taken, their images, and we can synchronize them, then we can go back and put them back together. And that's what this is doing. It's using atomic clocks to determine exactly when the images were taken, and then combine everything together. And they involve hundreds of scientists over 80 countries. And they use a technique known as VBLI, interferometry. Interferometry. I should know this. By acting together, they effectively produce an Earth-sized telescope, and I'll explain a little bit further in a second, to improve the angular resolution down to 21.6 micro arc seconds, which is well within the tolerances to be able to see an M87 black hole. So image processing, it requires a huge amount of data that it produces. So you got, in the first image that was taken, 8 of these telescopes were used. Okay, so, and the data is just too much to even transmit over the internet or a private internet or however you want to do it. It has to be physically, the data packs, the hard drives have to be sent back to a central location. So the radio telescopes collect data on a black hole. They do some digital processing, and everything is synchronized using atomic clocks. The hard drives are then flown back, and then they're synchronized back, and then the data reduction occurs, and an image is then generated. So there's a specialized set of software designed around a new type of grid computing system environment, supercomputers. All kinds of new imaging software had to be developed to do this. It took 10 years before they could get out there for the first images. And the data itself is still incomplete. Remember, we've got a few points all over the Earth to make it look like it's one big giant scope. What do I mean by that? Look at the James Webb telescope. It's got all these 32 or 36 mirrors. Each mirror takes the same image, but at different spots. Well, imagine if that was the Earth and we had all of these different telescopes. If the entire Earth had 50,000 of these telescopes, it would look like the Earth was one big telescope. But here, it looks like a few of them but it's enough for us to start going out and generating images. So we use sophisticated computer algorithms to build and fill in the blanks. What do I mean by that? So as the Earth rotates, data is collected. As it continues to rotate, a little bit of data, images, this is much later down the path. As each of these satellites, as each of these telescopes come into view, they collect data. It's a little bit more than what's shown here, but as you can see, you're not seeing the entire face of the black hole. You're only getting parts of it. And from this, you've got to fill in the gaps based on science, based on image processing, based on telling it a little bit about what general relativity predicts and so on. So before that was even possible, these were our artist conceptions of what a black hole looked like. And radio star, and the data itself comes out dirty. So cleaning the algorithm cleaning algorithm had to be developed, known as clean. Then each radio telescope was generating 350 terabytes of data, and each image is taken over 4 days. So over 4 days. 8 telescopes are involved. So a total of, for one image, 11.2 petabytes of data was generated to go out there and image one black hole and start processing it. The data was then sent to Massachusetts and Germany for processing. And the results were processed through what's called a radio astronomy RML image library, which has a whole bunch of thousands of different image library capabilities, and it looks for matching the best way it can, not of what black holes look like, but of cleaning it up and processing everything through that. And that results in the first jaw-dropping image of a black hole, which was this. Now, there's a lot you can learn here. First of all, why does it look like that and not an elephant or the Death Star? Because the data it collects, resulting in something that looks like the Death Star, doesn't make sense. You know, we know what looks more realistic, what actually makes sense, excuse me. And we have models that we can compare this with. As it turns out, our observation shows that, and our model shows this. Those are computer simulations on the right compared to our observation. So it's pretty exciting. And I'll talk about in a second. Do we still have time to finish this up?
Yes, we do.
Okay,
yes.
Good. I'll continue quickly.
Yeah, we can definitely take some more time and then go to questions.
So now, just to give you an idea, this is the galaxy. It looks like an elliptical galaxy. It's taken with an EV GOTO telescope, about a 4.3 inch, diameter lens. Lens. Back on in San Francisco on April 10th of 19. And as it turns out, when Hubble takes it, it's got the jets coming out of it, which you expect from the black hole, which helps a lot to orient things. But that was the black hole at M87. Let me tell you about our black hole real quick, and let me get back to that, what we learned from it. So at the center of our galaxy, in the Sagittarius, if you look out there at the Milky Way, and at the center is what's called Sagittarius A star. We have a bunch of X-ray images already, which tell us there's something there. We can use Newtonian mechanics and look at the orbital paths of various stars to see they're orbiting something we can't see. In fact, Nobel Prize was given for this. Look at this from 1995. And these are actual stars who we can look at the spectra of and determine mass and speed. And based on that, we determine that whatever is here that we can't see correlates to a 4 million solar mass gravity well. We can't see it, but there it is. There's a black hole there. So now we did that, and then used the Event Horizons telescope And the angular size from Earth is 52 micro. So it's well within the tolerances of what we can see. So here's the first image of the Sagittarius A star. And you'll notice here in a second that it looks a little more blurry than the one that's 55 million light years away. So M87 is much farther than Sagittarius A star. So why is it clear? Well, Sagittarius A star is also much smaller. It's 4 million versus 6.5 billion solar masses. If you look at it, M87 is its event horizon is bigger than the entire orbit of our solar system, our entire solar system. Whereas the accretion disk, or the black hole itself, the accretion disk here, goes way out there, is just out to Mercury's orbit for Sagittarius A star. But Sagittarius A star is harder to image because matter rotates, it's rotating much faster, so it comes out a little blurrier. When in the accretion disk, in the M87, it's taking it upwards of 2 weeks to go around at a high percentage speed of light given its size. In Sagittarius A star, it's happening in a matter of hours. So there's that, if you don't use the right kind of ND filter when you're photographing a waterfall, it looks all blurred out. Well, here's the situation here. The visibility directly to the center of the galaxy is obscured by dust and gases and other stars. These dust and gases absorb ultraviolet rays and other things and re-emit them sometimes as radio waves that these radio telescopes have to be able to clear out. So it takes a lot more work to do that. And so that's a big deal. Both black holes are imaged about the same time, but the Sagittarius A star image took an additional 3 years before we could show it to anyone, before that data was available. So now what you can see is a few things here to note here. These bright spot versus the dimmer spot is known as relativistic beaming. The gases are moving as they approach you. It's kind of a Doppler effect. They're brighter versus moving away from you. Similar type of thing occurring here, except this thing is rotating so much. This is an averaged out image. So you're seeing a couple of these show up on average because they're going around so fast, these hot zones. But the brighter one probably is the one that's approaching you more, and the other ones are going away further. This is a false image, by the way. The color is not orange. What happens is it comes out more in grayscale once it's converted from radio waves. But it's hard for the human eye to detect subtle changes in terms of what's bright, what's brighter, not what's dark and what's light, but what's bright and what's brighter. And generally things that are in the infrared or below in wavelength, longer wavelengths, we color them more this orangish. That's why those stars images that were taken by James Webb come out orange the way they are. So keep that in mind. These are all false images. But there's a lot to learn, including general relativity. It turns out what's going on here is consistent with general relativity, which is a big deal. So astronomers are looking to image more black holes. We have to go out there and find them, look for their telltale signs. Again, its effect on other stars and the birth of a black hole after a supernova or a failed supernova. EHT's footprint will increase with time. Currently, since 2018, they've had 3 more telescopes, so it's up to 11 now. And the ones in blue are brand new, up here in Greenland, France, and another one in Arizona. They're so close to each other, but that improves the fidelity of the images, as opposed to just trying to get more and more area coverage around the planet. Future possibilities for the Event Horizon Telescope. Well, we can go from 1.3 millimeter wavelength down to 0.87. and that'll improve the resolution quality. You're not going to go down much more than that. Below 0.1 millimeter, it'll be impossible to separate out the data. So we're not going to, there's no desire to go down that much further. Improve current image processing with more advanced algorithms. These are false images. We want to improve on them. You tell it about general relativity, but not too much. You don't want to, be biased about it. But if you take out general relativity from the algorithms, it turns out the images, when it fills in the gaps, are static. So, on top of that, what the most critical thing to understand is we are a spiral galaxy with a smaller black hole, and that's 27,000 light years away. M87 is an older, bigger galaxy with a much larger black hole. And guess what? They look essentially the same. They look very similar. That bodes well for our ability in our algorithms. Plus, these algorithms are tested against known astronomical objects that we know about. Eventually deploy a space-based event horizon telescope, which should help clear things up even better. I'll try to skip this. Until then, we go do things like look at how stars are shredded, but I'll move along because I know we're out of time. So once again, general relativity rules, that's the biggest thing. And, Einstein is correct. And I know kind of went by fast, but I wanted to cover a lot of things, some of the baseline and onto what the EHT is capable of doing. And I hope you guys found that interesting. I'm happy to take any questions. My email address is acm@firstcode.com, firstcode.com. It's on the first slide. And feel free to email me if you want. But I know I've gone a little past the hour. Are there any questions?
Thank you, Awanish. That's fine. We tend to go over sometimes if the topic is very interesting. Well, I'm checking the YouTube channel if there are any questions, but as for everyone on the call here, if you want to just unmute yourselves and ask the question, that's fine. Or if you want to put it in chat and have me ask it, then I can do that as well.
Or maybe there are no questions.
You answered it all.
Well, I hope you guys found this interesting. I love this topic.
Yeah, definitely. No questions, really. I'm just going to check the YouTube channel once. It's really quiet today.
Fair enough.
Let's see something in the chat here.
I love your presentation, how our distance is calculated. Well, I'm assuming you're talking about distances to black holes, but within the galaxy, there's several methods, okay? You can use triangulation, which is direct measurements, works well within the galaxy, works well on astronomical unit terms. Then you can use type 1a supernovas, which are very well known. You can use Cepheid star methods to get out further into the galaxy. You can use Hubble constant. I got a whole presentation just on that, but you're also looking at Doppler shifts further and further out when you're dealing with the Hubble constant and things like that. But let me give you one piece of information here. You take something like, when you look at an object, like stick your hand out and you go look at one eye, and then you notice it shifts. That's triangulation. So you can look at the angle and then you can calculate using basic trigonometry how far away your thumb is. Well, you can't do that with a star that's 600 light years away. But what you can do is image that star here in June, and then when the Earth is on this other side of the sun, image it again in December. Then what you've got is 93 million times 2, 186 million mile wide eyeballs instead of 3, and you can go out to 1,000 light years. Boom. So, but that doesn't get you to Sagittarius A star. And then you build upon it with Cepheid star systems. They explode with a certain brightness, and they have a certain period that they oscillate their explosions, and that period is tied to absolute luminosity versus apparent luminosity. And if you can correlate the two between apparent and absolute, then you can get distance, right? If I know how bright it is at 1 foot away, then I look at how bright it is at 10 feet away, and I can look at the two, and there's a simple equation, 4 pi something, to give you how far away that is. And you just build upon these things. The operative thing here is you build one upon the other. And so that's how they do measurements. I got a whole topic on that. Any other questions? Amazing, thank you. I appreciate the kind words. It's easy to stump the chump, by the way, and I appreciate you not doing that. Recently saw black holes colliding in the news. How much does one go about reasoning it? Oh, well, when 2 black holes collide, you end up with a bigger black hole. But what's really interesting is, more than black holes, is if 2 neutron stars collide. We had one collide in 2017 that was 1.1 solar mass 1.3, and guess what it produced? 50 Earth masses of gold, 200 Earth masses of platinum, so many other thousands of Earth masses. Who cares about a few million Earth masses? These things are on the order of the size of suns and bigger. So they produce elements. You get similar types of things occurring here. As black holes impact each other, the material is spewed out all over, and you get nucleosynthesis and all this, but you end up with a bigger black hole. And having its own, a new one with its own big singularity. Heavier. Black holes can die, by the way, but that's another time. If you look up Hawking radiation. Any other comments, questions? And I really love this topic, but I appreciate the kind words that several of you have given me.
So I don't know if this is a fictional concept or like, I don't know much about this, is what I'm trying to say. But there is a concept of the term I have heard is wormholes.
Yes.
Can you talk a little bit about that?
Sure. So when you're dealing with at the upper edge of all this stuff, dealing with the grand unification theory, string theory, M theory, dealing with multiverses, multidimensional stuff, part of in some of this esoteric stuff, and it goes back to Einstein also. That guy had everything together for us. He predicted wormholes as well, and what wormholes are is they're theoretical, mathematical. We've never found one. We better find one if we ever want to get out of the solar system. And, because unfortunately, that speed limit is going to be a big problem. But what a wormhole does, it allows you to basically cut through a conduit in space-time, creating what's called an Einstein-Rosen bridge from 2 different locations that would be on the order of light years, millions of light years, in a very short period of time. That's sort of the easy explanation, but it is highly theoretical. For us to be able to test it on Earth, it would take things approaching Planck energy, which that means is about 100 quadrillion times the energy output of the CERN accelerator. And if we wanted to do that, we'd have to build a CERN accelerator the size of our galaxy. So it's not something we're going to be able to go and build wormholes at will, but do they naturally exist or don't they? Who was it? There was an author who said this: if it's not forbidden, it'll certainly happen. So somewhere out there, it's very possible. I don't know what else to say about wormhole off the top of it, but
Oh,
it's more than science. It's more than science fiction. There's a lot of stuff.
Like I've come across it mostly in like science fiction stories saying how they connect different universes and like how it's a tunnel that you go through and like, you know, things like that.
But the problem is, how do you keep a wormhole open, right? So mathematically, you would have to use anti-gravity that would open it up. But we haven't even found the graviton particle. We don't even understand gravity because its strength is like on the order of 10 to the minus 39 compared to the strong force. So it's a very tough thing to understand. We don't understand gravity well enough, let alone manipulate it like they do on Star Trek or build wormholes. By the way, if anyone has ever read T.C. White's The Once and Future King, the quote is, "Everything not forbidden is compulsory." So if wormholes could exist theoretically, then I say it's out there somewhere. We just got to find it. I just don't believe in aliens until I see it, because that's how science works. Anyways, I digress.
Yep. Let's see. I'm gonna check YouTube channel.
Bring it on. I can answer anything.
Yep. I see Richie on YouTube channel reposted their questions, but those were already answered. So if you go through the video, you should be able to find those. And I see
quasar a black hole? No, it is not a black hole. It emits more energy than it looks like it should be able to, but it's not a black hole. It's not the other end of a black hole leading to a white hole. It's not. It's just that it's a naturally occurring object out there.
Cool. Well, I think that's all of it.
Okay. No, well, I love this.
I'm glad you liked it.
Yeah, and I got to tell you guys, I was pretty nervous about this because I didn't know if you're all physicists and engineers who were here to beat me up, or if you're, if I didn't want to make it too high, too low, just trying to find a sweet spot. And hopefully it was, but it is something I'm passionate about. And not that anyone cares, but I'm now exploring getting a PhD in nuclear astrophysics. So I'm interested in, I'm only 60 years old. I can start over. I retired just so I could go do that.
It's never too late to start over. That's for sure.
That's right.
Yep. You just got to start.
Okay. Any other questions?
What would happen if I had a bucket of antimatter?
Well, one, you wouldn't have it in a bucket. It would have to be contained in a magnetic field. Otherwise, it would interact with matter. Here's the interesting thing. After the inflationary period, before the inflationary period, when the universe came into being after the Big Bang, everything was energy. Then it started turning to matter. They were popping in and out, but there came a point where matter and antimatter annihilated each other. But for some statistical reason, we don't know, our math doesn't tell us this, 1 out of 1 billion particles were left over was matter. That 1 out of 1 billion collisions where they annihilated each other resulted in all the material in the known universe. Every star, every speck of dirt and sand on a beach, you, me, and all the burgers you eat, everything was all what was left over after that annihilation. So if you could, they can create antimatter, anti-electrons and all that, but it's on the order of numbers of particles that can cost billions of dollars to produce. It's not like Star Trek where they just build an engine and they all use antimatter. But it would be a very difficult thing to produce. And if you had it, it would come in contact with any matter. If it did, it would immediately annihilate it and turn it into pure energy. Remember, matter can neither be created nor destroyed. Neither can energy, right? You learned that in 4th grade. Conservation laws, but you can't convert between it. And that's what happened. When the universe cooled down enough, energy converted back into matter and things formed. But antimatter will completely annihilate it immediately.
Right.
I won't ask you how you got your antimatter either. Oh, what if you threw the antimatter into a bucket? Now that would be an antimatter that would be like negative, going into. You could increase the mass of the black hole, but worse, what happens if you were to eliminate matter into energy and you reduce the mass of the black hole, which is what Hawking radiation results in? In a vacuum, nothing is empty. Virtual particles are created, matter, antimatter, but conservation laws are not violated because in an instant they're created. This is what Stephen Hawking theorized there. They annihilate each other. But if on the edge of at the event horizon, if these pair particles created and the positive particle went this way and the negative particle ended up inside the black hole and couldn't escape because it was past the event horizon, now you've reduced the mass of the black hole. And if you reduce the mass of the black hole, it'll eventually evaporate. That's how a black hole dies. But it may take it 10 to the 50 or 60, maybe a Google years before it'll die. But that's what Stephen Hawking theorized, and they're working on trying to prove that, and I think he's probably correct. So that's actually a deep question. If I was to chuck a bucket of antimatter into a black hole, I need a couple glasses of whiskey and we can have a deeper conversation. So call me.
We can arrange that next time. I think let's call it a night. It's called that the last question of the night.
Okay.
Because we need to also relieve you, give you a break. You have been talking for a long time.
Yeah, you should talk to my wife. It never shuts up, as people say.
But thank you so much once again for joining us to give this talk. And thank you for all who attended, and hope you enjoyed it, and have a good night. And please join us again.